the last time we have talked about regarding the working mechanism of the dye-sensitized solar cell. And today we will finish this chapter, and then we start to talk about the next chapter regarding the energy harvester nano generator. So I just give a briefly recall regarding the most important component. So the first component is the dye, okay, the dye molecule, and then the titanium dioxide, okay, and then electrolytes, okay, and the PT. PT is the catalysis, okay. So all dye, PT, and dye, PT, and the electrolytes. These three components can proceed with the reduction and oxidation process, except titanium dioxide, because the dye can provide the electron, right? We know the dye can provide the electron. At the ground state, okay, at the ground state, promote the electron to this is the HOMO band and then to NUMO band. So electron provide to the conduction band of the titanium dioxide. So at this moment, because dye provide the electron, okay, so therefore dye become the oxidation state, right? Oxidation state. So dye need the electron, right, in order to reduce to the ground state. So this electron is very important that we need, making the electrolytes to provide the electron to the oxidation state of the dye. If the electron is provided from the NUMO band's electron or titanium dioxide's conduction band of the electron, and that means it will become a recombination. So that we don't want to see, right? This will become the gap reaction. So therefore, the electrolytes highly react to the electrolytes. Very important to reduce the oxidation state of the dye. Okay, become the ground state. So therefore, this reduction reaction is quite important. And then because the dye, the electrolytes provide the electron to the oxidation state of the dye, and still this I3 become the oxidation, right? Become oxidation state. So therefore, the PT is a catalyst. Need to provide the electron to the electrolytes. So therefore, become the reduction state of the electrolytes. So this is like a chain reaction. Okay, it's very, very important to each step. Okay, so as you can see, from here to here, and this is one step, and then second step from the NUMO band to here is the second step, and then the external electron flow to the external load is the third step, and from here, PT to the electrolytes is the fourth step. And then electrolyte to the NUMO band of the dye is a 5 step. Okay, so each step is very important. If we wanted to make the electron float for a forward reaction, okay, if each stage has a longer, I would say, very important is something like a rate controlling state. I would say the rate controlling state. So the rate controlling state is quite important. So therefore, the electron promote from the dye, we have shown you guys these figures. Okay, last time we have also talked about. From the NUMO band, from the HOMO band to the NUMO band is around nanosecond, approximate to 60 nanosecond. Okay. So that means that AB 60 nanosecond can promote electron to the lumen band, okay, to the lumen band. And then every 50 femtosecond to 1.7 picosecond, it can transfer the electron to the conduction band. So that means that the frequency is very fast, right? So we don't need to worry about that the electron being blocked at this stage, right? Because this transfer is fast. If this transfer is too slow, then the electron promote to the lumen band. That becomes a rate control state, okay, for this stage. Okay, so this is very important to justify, to determine about this state. Okay, and then now is although the electron can transfer to the conduction band of the TR2, but still you have to be very careful is the conductivity of the electron, right? Conductivity of the electron. So the electron need to transfer, and the conduction band needs to transfer to the external load, okay? To the external load, that means that the ITO glass, and then to the external circuit. This is like a circuit. So therefore, if there is some of the defect, or I would say the impedance of the titanium dioxide, if the impedance is too high, and that means that the electron will be blocked at this stage. Okay, so that's become a problem. Okay, become a problem, making here the electron will be combined to here, and then maybe to be combined to the electrolyte as well. Okay, so this is the important. So the stage, I think you guys should be understand about that. You can see this is like the sandwich. Okay, the device is quite simple. This is sandwich structure. Titanium dioxide is a nanoparticle, and then you can spin coating on the FTO. Okay, fluorine dope tin oxide. This is a conductive glass. Okay, so the nanoparticle size. Okay, and then for the TR2, we immerse, okay, with the electrolyte. With the dye. So therefore, you can see the TR2 surface in coating the dye molecule. Okay, it become, for example, as some of the red color, and then this is the HOMO band and LUMO band of the electrolytes indicate about that this electron transfer to the electron transfer to the conduction band. And then the next step is fill the electrolytes. Okay, fill the electrolytes. So therefore, inside of the electrolytes is a liquid state. Okay, provide the electron to reduce the dye. Okay, and then pack together. Okay, pack together. So therefore, this is a very initial, this technology has been developed in 1996. Okay, 1996. 1996 already there's a first dye-sensitized solar cell discovered by Professor Michael Brezel in Switzerland. Okay, EPFL. So this is the first solar cell, for dye-sensitized solar cell. And then, so therefore the package is very important because the liquid state, okay, liquid state of the electrolytes. So you have to be very careful about the evaporation of the electrolytes. Okay, evaporation of the electrolytes. Okay, so this is the first stage. You can see electron promote to the conduction band and then flow to the external load. So then to here, and then this electron will react with the PT. Okay, PT provide the electron to the electrolytes. So that's the train reaction. So if we compare about the working mechanism of the P-type and N-type junction of the silicon, so it is it's also similar, but the structure is completely different. If we look about the P-type and N-type, you can see there is a junction. Okay, it's a junction that we have mentioned in last chapter, right? Because at this junction provide the depletion node, right? So this depletion node establish internal electrical field, right? Internal electric field. So this internal electrical field is provided to this direction, right? To that direction, right? So therefore the electron can flow to here, right? Okay? Right? We already discussed about that, right? Internal electrical field is this direction, right? Is that okay? Okay, this direction. So therefore the electron can flow to this way. So same as for all the thin film solar cell has the same working mechanism. For solid state, photovoltaic, for solid state photovoltaic. And for the dye-sensitized solar cell, for dye-sensitized solar cell, you can see it is the sandwich structure. So if you look at about the absorption, okay, the dye looks similar to the p-type, right? Dye is similar because dye absorbs the light, right? Right, promote the electron to the luminal band. Luminal band is the excited state and send the electron to the conduction band of TR2. So this looks like a p-type, okay? Dye looks like a p-type, okay? But just the difference is inside there is an electrolyte. So I would say the mechanism is the same, but the very careful is that there's I would say some weakness. Okay, it's an electrolyte for solar for DSS because the electrolyte is you have to concern. The major concern is about the long-term stability issue. Okay, long-term stability issue, and this is the liquid state. But if compared to the price, cost, okay, TR2 there's all the process, okay, for the DSS, all the process is under ambient air, right? Under ambient air, that means you don't need to sputtering system, you don't need some of the furnace, no sputtering system, and then no vacuum systems. But for the solar cell, right, you have to deposit. If you have the p-type silicon, first the p-type silicon, you have to pour the single crystal, right? Pour the single crystal or polycrystal. You need a furnace, and then you have to increase the temperature over than 40,000, right? 400 degrees, right? In order to get the crystalline silicon, right? And then you have to pass through the purification process to get the 6N purity, right? And then even more higher, okay? And then you have the p-type silicon substrate, right? You have to deposit n-type silicon, right? N-type silicon. And then you have to proceeding with something like a tetra structure, right? To create the high surface to volume ratio of the surface in order to get the high absorption surface on the solar cell surface, silicon surface. So the process is still, I would say, for the silicon solar cell still need some of the process. But more advantage of the silicon solid is a solid state, so it can suffer very for a long time, at least 20 years. Okay. So we already talked about this mechanism, but here please remember about the key point about these 4 points. Okay, 4 points is that the major advantage of the DSSC you can see is a high surface to volume ratio of the TR2 photoanode. right? So each of the nanoparticle can deposit the monolayer of the dye, right? The monolayer of the dye. So it can act like each particle you can regard as a single solar cell that can provide charge transfer. Okay, but the nanostructure provide high surface to volume ratio, so you can see there is a huge amount of the dye molecule, right, absorbed on the TiO2 surface. So it can regard as just a tiny solar cell that can provide the charge transfer. So therefore, if we can manipulate the surface, TiO2 surface, to maximize the absorption line, also the absorption edge, which can create a high charge transfer process. But this is reliant about the technology that we have to do. Okay. And electrolyze, okay, electrolyze. And the proper working here, properly electro working potential HOMO and NUMO. What does it mean? Properly doesn't mean the suitable. Okay, the suitable HOMO band and NUMO band, which means because the TiO2 conduction band and valence band is right in this position, is fixed. But today, if you change the materials, for example, tin dioxide, or like copper oxide, or something else, metal oxide, the valence band and conduction band position versus the vacant state is a difference, right? The vacant state will be different. So therefore, you have to special design another dye to suitable for these materials. Understand what I mean? So you cannot use the same dye, right? You have to design to match about the N type of materials. Okay. So this dye is a nazerubin. Nazerubin, we call N, there's some N719, N719. This is the scientist in Professor Michael Brazil's lab, so-called nazerubin. This is an Indian guy. He developed the N719, which is already published in 1996. So this is because the HOMO band and NUMO band is special design for this titanium dioxide. Okay, so you cannot too high or too low. Okay, so you have to design a suitable electrical working potential. Okay. And of course, high efficiency catalysis of PT electron. Okay, so-called high efficiency. That means you have to create a high surface to volume ratio. See, at this PT. Okay, provide the surface, high surface. For example, PT is right here. If you provide a thing, a pin, looks like that. Or you provide a nanoparticle. PT. There's a significant difference because once we immerse the electrolytes to the PT surface, right? High surface to volume ratio can fully high surface to volume ratio of the PT particle can fully contact with the electrolytes, right? So it can react, provide the electron to the oxidation state of the I3 minus, right? But for the PT, if there's only thin leg, okay, only thin leg, the electrolytes has a limitation to contact with the PT simply, okay, with the PT simply. So this has a limitation, but here, high surface to volume ratio in the PT particle is even better than thin film structure. Okay. So high efficiency. Okay. And then fast reduction and oxidation with the high thermal stability of the electrolytes. Okay. So-called fast reduction and oxidation. The fast reduction and oxidation, that means here is a ground state. Ground state of die. Excited state of the die. Okay. But once the electron promote to here, it becomes oxidation state. So therefore, I would say the faster reduction, that means the electron transfer in the liquid state of the electrolytes must be faster. Okay? If faster, that means that the delivery electrons should be faster. Okay? So therefore, you can see here is about 110 nanosecond average if the electrolyte, this is the electrolyte, okay, 110, okay. So if you look at about this electrolyte, if we can deliver maybe less than 100, which means you can send the electron to the oxidational state of the die, it's very faster, which means the reducing state and oxidation state will be faster. Right? Just like a shooting, right? Like a shooting. So you have to provide a bullet, okay, fast. Okay, so this is a mechanism, and then the homostate on this homo band and normal band that we already discussed about that. So this is a reaction process, okay. Overall, the reaction process, please remember about that. S start denote is excited state. Okay, and S plus oxidate state. And I minus is reduction state. I3 minus oxidation state of electrolyte. Okay. So this is the balance you can make yourself to balance about the equation. Okay. So finally you can have get this reaction. So the so-called the die need to reburn. Electrolytes also need to reburn. Okay, that's very simple. Okay. Okay, so this is the summary working mechanism. Okay, summary working mechanism. I have mentioned. Okay, let's read about it. Lye is solved by monomolecular. Here, as we mentioned about the monomolecular. Okay, monomolecular. Why we need a monomolecular? For example, this is the particle of the PL2, right? And then here, it mentioned that monomolecular. Okay, this is a die. Monomolecular. Why we need a monomolecular? What about multi-molecular? Can we have a multi-molecular if we absorb more dye? Which means that the dye can absorb more light, right? And send the more electron to the TL2. Why not? We need a monomolecular. This is CD and this is BD, right? And here electron sending. What about your opinion? Do you know my question? Here, light is absorbed by a monomolecular layer of the dye chemical salt, right? Later on, I will show you what is a chemical salt. But the question is monomolecular, that means it is the mono layer, right? Not the multi-layer. But now I want to ask you, if we can provide more molecular, that means multi-layer, 3 layer, 5 layer, 6 layer, and even more, right? Oh, here I need the dye. Okay, dye. Is that okay? If I ask you this question, then maybe this is not okay, right? The answer is not okay, but the question is why? Right? The more, the better, right? The more better, the more money, the better, right?
The extra layer will block the light, so light cannot touch the inner layer.
I think this is not major, right? The more light, okay, the more light, because inner layer, yeah, maybe if you have the more dye, right? The inner layer maybe is the light being blocked, right? But still, you have high surface to volume ratio of the dye. You can absorb more light, right? You still can absorb if you provide more dye. You still can absorb more light, right? Although some of the inner layer may be blocked by outer layer. Yeah, this I know your opinion, but still the major issue is the point. So why we need a mono layer, because it emphasizes the mono layer, which means the multi-layer would be bad, right? Multi-layer will be more worst case, okay, compared to the mono layer.
Is that dye a conductor?
Conductor.
If not, the outer layer, the dye in the outer layer will not conduct the electron into TL2.
TL2. Yeah, I think mostly 99%. Okay, you get the point. Okay, so the point is you can see here the electron transfer to the TL2 conduction band, right? So look at about here. If electron transfer to here, if you have another dye, for example, you could see, oh, okay, here, for more electron to here. but electron transfer to here, right? The conductivity is completely different, right? And then the HOMO band and the LUMO band is the same, but you have to transfer to here. So dye is not provide a high conductivity. Dye is provide the visible absorption edge, which is able to make the electron promote from the LUMO band or from the HOMO band to the LUMO band, right? So dye is the functionality is just like a p-type, okay, just like a p-type, which is absorb the light, right? Absorb the light, promote the electron to the conduction band. So the functionality of the dye we cannot design for high conductivity. Do you understand? So therefore, the electron will be blocking here. Okay? Here, the first step, electron promote to the LUMO band is no problem. But the problem is the transfer. There is a problem. And even if you have the more, right? You have the more electron, right? Sorry, dye. And then still, from the electron transfer to here, they become a low impedance, higher impedance, right? So therefore, TL2 just waiting there. There's no electron being absorbed, right? So therefore, that's become a rate consuming state at this stage. So when you're doing such research, you have to be very careful. You cannot absorb the light, the dye too long. Otherwise, you will accumulate a lot of the dye molecule on the surface and then block the electron at the interface. All right, the interface. So, and then chemical assault, okay? Which is a chemical assault. Chemical assault, later on I will explain, okay? Do the same thing, how promote the electron that we already discussed. And then Ruthenian dye, okay? Ruthenian dye, this is a Ruthenian dye. There's a lot of the metal dye. Basically, is a Ruthenian dye, okay? So excited the electron then transfer very short time, pico to the phantom from here to here, okay? Into the conduction band of TL2. So this lead effective charge separation, with a negative charge within the titanium. Okay, this is the TL2 phase, and the positive charge on the surface of absorbed within the dye. Okay, so this becomes the positive. This is Ru3+, that means the oxidation state. Okay, because become the oxidant, right? 3+. This is 2+. Okay, 2+ is a reduction state. 3+ oxidation state. Okay? Okay? Oxidation state. So 3+, Ru3+ is then reduced by very rapidly within nanosecond by receiving iodine and I3, I-, right? I-. So I here, this is I2+, so it's too small. Here. Okay, this is Ru2+ and 3+, right? 3+ is the oxidation state. 2+ is a reducing state. Okay, reduction state. Okay, and electron to 3+. Okay, this is I3, I-. Is that okay? I-. Here is the PT standard electron. Okay, and then electron inject to the TL2 in the previous state, diffuse, okay? Okay. Through the network of particle until you reach the conductive surface for current conversion. So therefore, once the electron transfers through the TL2, it becomes a long journey, right? Long journey, that means that there's a long road. So we have to make the electron transfer in the TR2 as possible, as soon as possible to reach the conductive ion, conductive CD. Okay, conductive CD. So the conductivity and also the impurity is very important. Okay, it's very important. Okay, and then the electrical charge does actually from the photoenol, from this side, photoenol, as the current can be utilized for use, for external use. Okay, power. Okay, and then finally reach the complete state. So you can see, in order to cross the circuit, the negative charge are directly to the surface of the contact electron. CE, here is the CE. Whether I3 minus is reduced to the I minus, that means here the PT, right? There's an external electron here, right? External electron is external. So provide electron to PT, so send to reduce I3 minus. So this is quite simple. Okay, so as I just mentioned that the dye has example, for example, N719. Then now there's a lot of the dye, but this is quite representative. The dye representative so far, because it is the very beginning. So you can see this is the absorption edge of the dye. You can see here. Okay. As you can see, there is a COOH bond. COOH bond right here. Okay. This N719 provides COOH bond. Okay. The functionality of the COOH bond is one or two. You can see different style. Leucinium has a different COOH. This has a COOH, 4 group of COOH. This is 4 group of COOH, which means this look about right here. This is TR2. TR2 has a TROH. Leucinium dye has a COOH. So COOH can combine with TROH. So therefore the OH bond will release, dehydrogenate. Okay, dehydrogenate. So therefore become the TiO2. This is double bond C. Okay. So this is the chemical bonding. Alright? Because the OH being dehydrated. Dehydrated. So therefore dehydration. So therefore become the chemical bond. This can be tightly bound on the TR2. Okay. And then if next dye come to the mono layer of the dye, which is only just physical bond, okay, physical attach. There's no chemical bond, okay, no chemical reaction, so no chemical bond. So you can just use some ethanol or some of the solvent to clean the extra dye from the surface, okay, from the surface. So it then become a mono layer, okay, become a mono layer. So as you can see, different Leucinium dye, it has the different absorption edge. So we want this absorption edge as longer as possible. So therefore, you can cover the whole visible range of the solar spectrum, right? That's better. Okay. So remember about that TR2 is absorbed only is the absorption edge is 380, right, nanometer. So TR2, the functionality TR2 is just only provide the surface for dye to absorb on their surface. So it does not to provide the electron. Okay. So TR2 no need to provide electron. The provided electron is from the dye, right? And dye provides the electron to TiO2. Okay, so I would say they are just like a partnership. A partnership. TiO2 is right here, dye is right here. So dye, the functionality is absorb the light, right? Promote the electron to TiO2. TiO2 transfer to the ITO, okay, and then to the external circuit. So therefore, the functionality of the dye, we have to design as longer wavelengths as possible, and then we can cover the whole spectrum. Okay, cover the whole spectrum. So this is one of another advantage to compare with the solid state of the photovoltaic. Because solid state of the photovoltaic is just only one absorption edge. For example, here silicon is 1.1, right? So the absorption edge will be maybe 600 to 800 nanometer, right? Nanometer, something like that. So it cannot cover the whole range, right? Cover the whole range. And then, for example, another material, CIGS, copper, indium, selenium, gallium, sulfur, something like that. It is also another absorption edge. So you cannot have having one materials can get whole spectrum, right? It is impossible so far, unless you provide a tandem structure. Tandem structure, that means one layer is one of the materials absorb 1.1 H EV, another materials 1.3, another materials 1.6, for example. So therefore you have the difference there of the tandem structure. That is possible to cover full range. Do you understand what I mean? Right? But this is the cost that will be applied on the solar cell. Do you understand? For the solid state right now, there is a design for tandem structure. Tandem doesn't mean the multi-layer, right? So you have the cell 1, cell 2, cell 3, right? And light can come through from here. So you can have, right? Cell 1, cell 2, right? Okay? So you can have it, also having the whole spectrum. Okay? But still you have to design, right? You have to design very precisely. Okay, very precisely. If there's a UV light, because they still have the UV light, right? UV light will making the whole spectrum being excited electron. Okay. But this will increase the cost. But this kind of the design, it is just based on your capability. If you are the high capability or the very familiar, okay, to design the dye molecule, then that might be possible to create another dye. This guy is so-called Nazarudin, okay? Maybe your first name, for example, my name is Wu Zhimin, right? You can create the Wu Zhimin dye, something like that. You can use your name as for the future, okay? For the future. Okay, so let's take a break, okay?